You know how it's impossible to really compare two completely different things? Like, say, an apple and an orange. Well, in the world of data, we have that problem all the time. But what if there was a universal translator? A way to put any number from any data set onto the exact same scale so we can finally understand its true meaning? Well, there is, and it's called the Z-score. Let's dig in.
Okay, let's start with a really simple question. Imagine you just graduated and you landed a job offer for $42,000 a year. So, is that good? Is it amazing? Is it kind of low? The honest answer is you have no idea. Without more context, that number, $42,000, is pretty much meaningless.
And that right there, that's what we call the apples and oranges problem. It's this fundamental challenge of trying to compare values that basically live in completely different universes.
I mean, think about it. How on earth does a college compare an SAT score of 1,500 to a GPA of 3.2? Which student is actually doing better? Or how do we know if the 11 million views for a show like Squid Game is a once-in-a-generation hit or just, pretty good? Or is a baby weighing 6.9 pounds big, small, or perfectly average? We need a common language to figure this stuff out.
And this isn't just a puzzle for us humans. It's a huge, huge problem for technology. Imagine your machine learning model. You're looking at age, which is in the tens, and income, which is in the tens of thousands. A $1 change in income is tiny, but a 1-year change in age is significant. The algorithm can't tell the difference. It just sees the bigger numbers in the income column and thinks they're way more important, completely throwing off the results.
So, how do we fix this mess? Well, we use a brilliantly simple tool that acts as data's universal translator. It takes all those different scales and puts every single number on a level playing field. And that tool, of course, is the Z-score.
The definition sounds a little technical, but it's actually super straightforward. A Z-score just tells you how far away any single piece of data is from the average. The key thing is, it doesn't measure in feet or dollars or test points. It measures in a totally universal unit called standard deviations.
And reading one is incredibly easy. If the Z-score is a positive number, your data point is above average. Simple. If it's negative, you're below average. And if it's 0, bam, you are exactly average. The number itself, whether it's say a +2 or a -0.5, tells you exactly how far away from the middle you are.
So how do you actually calculate one? Well, it's basically a 3-step recipe. First, you need the average of all your data. That's the mean. Second, you need to know how spread out your data is on average. That's the standard deviation. Once you have those two numbers, you just pop them into the formula.
And here it is, the formula itself. It looks simple, and honestly, it is. You just take your specific score, subtract the group's average, and then divide that whole thing by the standard deviation. That's it. That simple piece of math is our universal translator.
Okay, but this is where it gets really cool. A Z-score isn't just a handy calculation. It unlocks our ability to see a predictable, natural pattern that shows up almost everywhere, something we can see in the power of the curve.
What's so fascinating is that when you start measuring things out in the real world, things like human height, or blood pressure, or scores on a test, a really amazing pattern starts to emerge as long as you collect enough data.
You can see it happening right here. If you only have a small sample, the data looks kind of random and messy. But as you add more and more and more data points, a very clear, distinct shape starts to take form. Most of the values bunch up right in the middle, around the average, and then it tapers off on either side. You've probably seen it before. We call it the bell curve.
This is the normal curve. And the reason it's so important in, well, pretty much all of statistics is because its shape isn't an accident. It's incredibly predictable. It has rules.
And those rules have a name that's pretty easy to remember, the 68-95-99.7 rule. It basically says that for any data that follows this curve, about 68% of everything will have a z-score between -1 and +1. About 95% will be between -2 and +2. And almost everything, 99.7% of all data, will fall between -3 and +3. So a z-score doesn't just tell you where you are, it tells you how rare or how common your position is. It's amazing.
Okay, so theory time is over. Let's see what happens when we actually put this universal translator to work on that tricky machine learning problem from earlier. This is where we see standardization in action.
Just look at this transformation. It's incredible. On the left, you've got the raw data, right? Age and income living on completely different planets. Then we apply the z-score formula to every single number in both columns, and look at the right. Boom. Everything is on the exact same scale. The average for both is now 0, and the standard deviation for both is now 1.
And that's the magic trick. Now our computer can finally compare apples and oranges.
A 1-unit change in standardized age means the exact same thing as a 1-unit change in standardized income. The algorithm is no longer fooled by big numbers and can find the real patterns in the data.
Okay, that's awesome for computers, but what about us? How does this actually help us answer questions in our own lives? Let's bring this home with a really practical example.
Okay, imagine this scenario. You took 2 final exams. You got an 80 in sociology and a 68 in philosophy. Now, at first glance, the 80 looks way better, right? But hold on. A raw score doesn't tell you the whole story. You need context. We need to know how the rest of the class did. So the real question is, on which test did you actually perform better compared to your classmates?
Let's break out our universal translator. For sociology, you take your score, 80, minus the class average, 83, and divide by 10. You get a z-score of -0.3, so a little bit below average. Now let's do philosophy. Your score, 68, minus the average, 62, divided by 6. That gives you a z-score of +1.0.
And there's our answer, clear as day. Even though your grade was 12 points lower, your performance in philosophy was actually way better. You were 1 full standard deviation above the class average, which is a fantastic result. In sociology, you're actually a bit below average. The z-score told us the real story.
One of our sources really nailed it with this quote. Z-scores are a tool to help determine how a given score measures up to the whole distribution. It's not about the number in isolation. It's about where that number stands in the entire crowd. And the z-score is the tool that gives you that critical perspective.
So, the next time you see a stat, a salary, or a test result, just remember that the number itself is only one part of the story. The real meaning, the real insight, comes from understanding where it sits in the bigger picture. You now have the tool to figure that out. So, the only question left is, what are you going to compare first?